Okay, welcome back. We're going to have the second of three sort of what have we learned discussion sessions. We had one the first week that I thought went very well, and we'll have one at the very end of the school next Friday. Before we get into that, I received word that the t-shirts have arrived on campus. However, I was hoping we could hand them out now, but they seem to be caught inside the university mail system. And when yeah, a staff member is working to extract them, but I don't. There's no guarantees, so it may be Monday before we get the T-shirts. So, and those of you, the lecturers who won't be here, your T-shirt will be shipped to you. So. Well, I thought what worked pretty well last time was to just each lecturer to briefly go over what they discussed, just to refresh our memories, just a few sentences or so. And since we're actually covering 2 weeks, we'll start with Keith from last week, and then I'll try to say a few words about the other speakers last week.
Okay, well, thank you, Brad. So last week, 3 lectures with the theme being rotating convection. The first lecture, I pretty much lectured about a feel for rotation. So we talked about a lot of the GFD objects that were buoyancy driven and influenced by rotation. We looked at some elementary theories of rotation, the geostrophy and the Taylor-Proudman constraint, which acts against, non-hydrostatic or convectively driven flows. And we talked about the differences between forward cascade and inverse cascade, with rotation having the potential to generate inverse cascades in fluid systems. In lecture 2, we motivated Rayleigh-Bernard convection, looked at linear stability through the asymptotic limit, and we saw that actually motivated an asymptotic regime. And then we derived the quasi-geostrophic equations, and we did it from a general point of view. So we had Rossby number being a small parameter, and then we had a tunable aspect ratio, and then we went across all the scales and showed how you can produce the classical, stratified QG equations to the ones that we use in our work, which is the non-hydrostatic quasi-geostrophic equations. And in the last lecture, we looked at those equations in the limit of Rayleigh-Bernard convection, looked at solutions to those, and played with some. I displayed some of the nonlinear solutions that we got out of simulation.
So we had Hussein Alawi, who sort of took off where Grisha left off and began a discussion of turbulence. And that led on to a discussion of subgrid closures. So large eddy simulation, how that works. Antoine Vanay talked about the topological origin of certain waves in the Earth system, the equatorial Kelvin I waves, and then he spoke about the coastal Kelvin waves, and then I think he talked to some of you about his ray tracing program to try to better understand why there's this bulk interface correspondence in the fluid systems. Freddy Boucher talked about large deviation theory, and he began with a very simple model, this Kramer's model, the double well kind of potential, and illustrated the ideas there, these instantons that take you from one well to another. And then he went through a hierarchy of models looking at geostrophic turbulence, and then finally ending up with actual climate models trying to look at heat waves using some sampling techniques to increase the statistics for these extreme events. Yuhai Tu told us about active matter, and we heard about his famous work, John Toner, and from 27 years ago or so, and renormalization group views of transitions in active matter. And uh, and then for this current week, we had one lecture by Andy Lucas, who applied the ideas of hydrodynamics to electron fluids, thinking about those in graphene, for example, and talking about the various forms of viscosity that appear in that matter. Steve, why don't you go next?
You want me to talk about me or Alan?
Both.
Oh, okay. So Ellen unfortunately had to leave, and so I've been asked to summarize what she was talking about, but I don't, I'm not an expert, so please don't ask me any questions. So she was talking about how you can couple cosmic rays to fluid equations and get an equation, a fluid equation for both the cosmic rays and the gas. And then by the end, once she derived these fluid equations, she managed to demonstrate an instability called the Parker instability that was driven by the cosmic rays, which I thought was really interesting. That's all I can say really about what Ellen did. So I was motivated by geophysical and astrophysical objects to look at the interaction of turbulence with mean flows or mean magnetic fields. So I spent a lot of time motivating things, and then talked about how you might approach solving such problems by splitting, doing a Reynolds decomposition into a mean and fluctuating parts, and then try and derive some equations for the mean and the fluctuations. In lecture 2, I talked about the approximations you could make on the fluctuating equations, so-called quasi-linear approximation, and then the extension to what we call the generalized quasi-linear approximation. And we did all of this so we could write down statistical equations. So in lecture 3, I talked a little bit about how you might approach parametrizing either the Reynolds stress or the EMF, and then talked about a way of systematically deriving set equation sets for the low order statistics of a system. And by the end, we had this program, which we called direct statistical simulation, where we were solving hierarchies of cumulant equations.
Sure. So picking up on themes that Keith and Hussein started out last week, which I anticipated was going to sort of work. We revisited the equations that you might use for climate modeling, and particularly climate modeling in the ocean. So we talked about the hydrostatic balance, we talked about the Boussinesq equations, we talked about sound waves, we talked about 3 different kinds of small scale turbulence: mesoscale, submesoscale, and boundary layer turbulence. And then in that, we came to the conclusion that sure, the quasi-geostrophic equations are sort of asymptotically correct for the mesoscale, but not for the submesoscale. But even so, we still use the hydrostatic Boussinesq equations across both of those scales, because some of the climate phenomena, outcropping isopycnals and things like that, didn't really work so well in QG. And then we needed to break the hydrostatic approximation in order to get to the 3D turbulence within the boundary layer scale. So with that in mind, then we moved on to talk about how we might filter things across scales, which I hope pinged back to things that Hussein had talked about the week before. And we talked about spectral methods and filtering methods and then structure function methods, and then came to the conclusion that the reason why the key phenomenology of the submesoscale that was missing from the mesoscale was this convergence, surface convergences that brought all those drifters together into one spot. And so that isn't part of the quasi-geostrophic equations, or at least as normally construed. And so that was one piece. And then in closing, we jumped over to say, well, maybe we can partially resolve the mesoscale. So what would we have as the subgrid scheme for a partially resolved mesoscale? And so we talked about the Smagorinsky style of getting a closure, and then talked about how in quasi-geostrophic theory, you can make a closure that's similar, the quasi-geostrophic Leith closure. And then we saw some examples of how that worked. Then we talked about parameterizing very vaguely the submesoscale and Langmuir scale, or boundary layer turbulence scale, and showed that essentially those parameterizations, without a whole lot of details, do actually feed back all the way back onto the climate system. And so there's this, $10 trillion question of how much the Earth would warm under a particular amount of carbon dioxide emissions. And that boundary layer, at least when we break it down region by region, has something to do with answering that sensitivity question. And so, keep plugging away and making those parameterizations better is the takeaway from that.
So I just uploaded earlier today all my notes in one PDF file with an outline at the beginning. It's 218 pages. But so in 1 minute, exactly in 1 minute, what is the main thing I wanted to emphasize? Well, ostensibly I was talking about the transition to turbulence, but the real message was when you're doing physics problems or scientific problems, it behooves one to try to find the regimes where one can expect a universal behavior that can be explored by a judicious and artful choice of minimal models. And not all problems that you want to solve are in that category. Problems that Baylor was talking about to do with climate change, probably not. But on the other hand, those sorts of methodologies may have a role to play if one wants to understand large-scale statistical properties in the same way that Steve was talking about in his talk. So what I showed you was a variety of different minimal models, all empirically based, which nevertheless made predictions rather than interpolations. We're trying to do extrapolation, not interpolation. And the amazing thing is that if one looks near critical points, if one looks in asymptotic regimes of the phenomenon, one can often find attractors from which one can make minimal models that then give you a real fleshing out of the phase diagram of the phenomenon in question, and then the bits in between where you have to fit parameters and so on. That's not described so well by the methodology that I'm trying to espouse. And it's not just in modeling transition to turbulence. We've used this for 30 or 40 years in studying various problems in biology and material science, condensed matter, and so on. So I think I'll just leave it with that. If I want you to have one take-home message, it's that, as I wrote, it's completely mind-boggling that a partial differential equation solved digitally on a computer or analogically in a pipe filled with water behaves in a small range of Reynolds number like water drifting through your coffee percolator.
So this week, I think we reached our largest length scale. I had no idea that you could think about cosmic rays as a fluid. And possibly next week, we'll go to our smallest scale, depending on what Damson decides to do. He's thought about the quark gluon plasma, but I think he'll probably be more at the length scale of condensed matter systems. So with that, let me open it up to questions or comments or discussion. And we have a second microphone that you all can use, and then we'll pick up this microphone as needed.
So very loud. My understanding of like how this was brought together is that traditionally people didn't think of all these fields as being related by this idea of hydrodynamics, and then more and more people started to see that these ideas could be used in their systems. So I don't want to be like a negative Nancy here, but are there things that hydrodynamics doesn't work for, and is it useful to think about the distinction between systems where it works well and where it kind of breaks down? Besides, I mean, there's sort of an obvious category if you're looking really zoomed in at the granular stuff, it's not going to do a good job. But are there other distinctions that are useful?
Well, so one example that I touched on was the sea ice at the end, which sometimes behaves like a fluid when it's broken up and kind of flowing, or a marker of a fluid process, and sometimes acts like a solid when it resists compression and ridges up on itself. Those interfaces are interesting because the kind of solid fluid interactions in a strongly coupled system like that, where the ice could be melted by the ocean, or the ice could be melted by the atmosphere, or the atmosphere and ocean could exchange through the gaps in the sea ice, makes the polar climate system very different from the rest of the world. That's part of the reason why the polar climate system is warming faster than the rest of the Earth, is because it has this very different characteristic with sea ice involved. So yes, many things are hydrodynamics, but not quite everything. Not the pieces of that, pack ice, sea ice, definitely not. But it's important, even in these fluid systems, to think about the relationships between them.
Maybe I could add, there's a famous quote by a Greek philosopher whose name has gone out of my head. It could be Sophocles. It's pantapei, which is everything flows. So there you go. So they knew it back then.
I think we saw in Andy Lucas's talk that there were regimes that were more ballistic than hydrodynamic. So when looking at these mesoscale devices, you had to pay close attention to the mean free path and how that compares to the scale of the device. So certainly in condensed matter, we often are working in ballistic regimes, which aren't well described by hydrodynamics. But his work is kind of in this interesting area, transitional area, which seems like that could lead to some new insights about how to go from one description to another. Nigel.
So sometimes whether it flows or not depends on how well you look at it. And if you look at, say, the glass in the building, it's strong enough that if you run into it, you'll hurt yourself seriously badly. But on the other hand, if you run into it really slowly on a time scale of, say, 5,000 years, you'll just be able to walk right through it because it's actually a liquid on those time scales. So another message is whether it's flowing depends on your patience. And if you did a PhD thesis on glass, if you want your PhD thesis to finish in 6 years, you would probably be wise to regard it as a solid. If you're going to do your PhD thesis on a scale of, say, 10,000 years, it would be a PhD thesis in fluid mechanics.
6,000 year PhD theses only happen in the humanities, though.
I should say we're also open to questions about careers. I was thinking we would focus on that next time, but since these lecturers will be gone next week, you may have questions for them about that too. Yes.
Thank you. This is still not a question about career, but I'm asking about the diffusion treatment in Rayleigh-Bénard convection or other things, because we usually see Laplacian diffusion in many of the equations. But I'm wondering, could we, because we want to go to more extreme regimes with high Rayleigh number or high Taylor number, so could we use large eddy simulation to those already very idealized Rayleigh-Bénard convection, or shall we just not use second order Laplacian operator, but use fourth order or eighth order operator? And will that make this problem less classic, or it can be a direction to pursue? Thank you.
Well, I think in the literature that this is already being pursued when you're trying to get to really high Rayleigh number, Rayleigh-Bénard convection. And I guess the question there again is the classical closures, but in GFD, it's I think Beta was talking about Leith and QG, so it's not, those closures are not known, okay, and just doing the standard thing, doesn't really work, and trying to compare it with what is also quite an issue, okay, but that's being pursued. If you're doing the GFD community in terms of looking at the dynamo problem, most of those simulations are still DNS. when they entered the large eddy simulations, it's very crude. You know, they're still doing 3-dimensional Smagorinsky. And, you know, that's not right, you know, because these are highly anisotropic flows. Okay, so you have to do things where you're guided by what you know the dynamics of the problem is, like doing LEAF. And I have a graduate student actually looking at right now, looking at LEAF in non-hydrostatic QG systems. So you've got to play in, and again, there's nothing to really compare to. Unlike climate and the ocean, where you like a data-rich system, these systems are not data-rich. So, you know, you're really just being guided, you know, by what you see.
And I guess one other point, so when you first start out doing large eddy simulations, now there are a lot of tools like implicit LES, which are just, you know, kind of filtering operators that are in the numerics that don't really, they may not be the best thing you can do, but they don't blow up. So the property of Smagorinsky that's great is it doesn't blow up. And sometimes you get, you know, kind of misled by that to think that Smagorinsky is actually the right closure for your system. But there are lots of other choices of kind of other things that won't blow up. And you can play and kind of understand the dynamics in that large eddy regime without specify, and then go back afterward and think about how different closures might affect the results. So that's another approach to take it on.
I know you didn't ask about this, but if you were doing magnetoconvection or dynamos, just a word of caution, if you're looking at the induction equation, make sure you get the diffusion operator correct for the magnetic field, because the induction equation is different to all the other equations, because really it's just a competition between advection and diffusion. If you get the diffusion wrong, you get it all wrong, right? There's no balance, there's no pressure, Coriolis, anything else to come in, and it's advection, diffusion. Don't get the diffusion wrong, because then you get the wrong answer. An astrophysicist would do well to listen to this, but they never do.
I think this week we've heard about like stochastic models being almost like a subgrid scale model for parts that you don't like, small scales that you don't resolve in your system. But also I think we've heard about that as something intrinsic to your system, something necessary to include to get the right dynamics. So I'm a bit confused about these like seemingly contradicting views, and if you could speak more about that.
Who'd like to take that?
I get the noise question right. I think both of those, that's a great question. I think both of those scenarios that you outlined are valid under different circumstances. So in one case, if you start off with what you think is a deterministic equation, and now you are in a principled way trying to remove degrees of freedom so that you're just focusing on, say, large scale degrees of freedom, the effects of the small degrees of freedom then act as noise. I mean, actually, you knew this, you learned this on your mother's knee. You learned about heat when you learned about elementary thermodynamics. And of course, statistical mechanics applies to deterministic systems. But what is heat? Well, heat is just the degrees of freedom that you neglected to make your coarse-grained thermodynamic description. So that's one place where it arises, and that is a introduction noise as part of your mathematical description, just as you implied. I guess the other way is it can be intrinsic, such as if you have a system where it has, say, a chaotic attractor, or it might have another phenomenon that some of us are studying right now, which is known as spontaneous stochasticity, another even more strange effects than chaos. And there it's an intrinsic property of dynamical systems theory. So you can have both. I don't know if that's comforting. And then there's other things where this is a paper that we just published a couple of weeks ago. You might think, well, I've got Navier-Stokes equation, so I know everything that's happening at the short scales. But actually, what we showed that actually, if you look at the effect of thermal noise, actually it is noticeable up to the Kolmogorov scale and completely changes the behavior in the far dissipation range. So sometimes noise is there, should be there, but is not included. because people thought that fluid mechanics is purely deterministic, but at the smallest scales, there is noise governed by fluctuation dissipation theorems and so on. And then because of the nonlinear dynamics, it actually ends up affecting a much larger range of scales, well beyond the limit where hydrodynamics breaks down. So up to the Kolmogorov scale, and in fact, even into the inertial range, because of the way that intermittency interacts between the intermediate scales of the inertial range and the small scales in the dissipation range. So you can have also the other way around, where you don't put noise in, but you should have done. Does that answer your question? It's a what? That means no. Well, what were you hoping?
Talks about the thermal noise you talk about. Is this something measurable? Like the thermal noise,
Yes. Are you hot right now?
but I can't feel the fluctuation.
Well, sure you. Sure you can. You can feel pressure and things like this, right? Yeah, in principle, it's observable in the spectrum and in processes that merge microscopic and macroscopic scales like combustion and mixing and so on. So yeah, right now I don't think those effects have been measured. That's for sure. But on the other hand, I would also say that if you look at what the predictions are for, say, the energy spectrum and the far dissipation range, where people always assume that there's some exponential fall off in the spectrum, there's no experimental evidence for that either. Okay, so but if you think about the physics of it, it has to be that statistical thermodynamics didn't just disappear when you started doing fluid mechanics, and then it's a quantitative question: where does it enter? And then if you go and do the calculation, you say, holy cow, it stops at the microscopic scale where the mean free path of the particles goes into the hydrodynamic limit. It actually goes way, way into the hydrodynamics regime. That's the big surprise.
There's one other thing to think about with stochastic systems in a totally different context, which is, so using a stochastic injection on top of some subgrid scheme where you might have some kind of backscatter coming from the subgrid and putting noise into the system. And that seems like something you consider to be sort of an interesting toy problem, but from a very pragmatic aspect, if you're doing weather forecasts, we know that the weather system is highly chaotic. So in 2 weeks, you have no sign of your initial conditions anymore. And so you'd think you'd want the least noisy system you could possibly have as you go back to the beginning, because you'd really want to get, let that trajectory from the initial conditions go as far as it could before it destabilizes. But in fact, when you put it together with the uncertainty and observations, it turns out that you can make better forecasts if you add noise to the original system and then data assimilate into an ensemble of noisy weather models rather than one deterministic weather model, which is kind of a funny, seems a little bit backwards when you think about it, but it's a better representation of the unknown scales to have noise even at the resolved scale when you're trying to put that together with uncertain measurements of the initial state.
I just want to add something to Baylor's interesting comment, because it actually relates to a paper that we're just finishing right now, which is exactly on this. If you look at I'll ask the question, how long does it take for these thermal fluctuations to actually get into the flow? The answer is 1 eddy turnover time, or maybe 2, something like this. So as you said, there is a limit of predictability that is imposed by small scale fluctuations due to thermal noise, even in an atmospheric boundary layer. So as you said, if you take the coarse grained thing and then do ensemble averaging, that gives you better predictions. And there is a fundamental limit to that comes from the amplification of these things. So thanks for that.
Maybe I can say, people add noise for different reasons in different situations. If you have a shear flow, it's well known that the equations that you get are quite often not self-adjoint, and therefore there's a non-normality in the linear operator. And what you do is you transiently amplify any disturbance you give it. And so people are trying to understand, transition to turbulence using this framework, and what they think of is you have an input-output device, which essentially takes some noise, it amplifies it using, you get the eigenvectors of the non-normal operator, and then you just essentially pass things around this input-output device. And now people are trying to do an optimization of the form of the noise, which best gives you the feedback to give you the saturated mean flow that you would get to amplify that noise. So they see it as essentially as an engineering problem, a linear input-output device plus noise which you've tailored. So the noise is the whole turbulence, noise which you've tailored to give you the best answer. And they do that using methods of data science, optimization, perhaps deep learning, that kind of thing. So people talk about adding noise for different phenomena, and it's very model dependent.
So during this summer school, we hear many different topics. So I'm wondering in the later career, when and also when it's maybe a good choice to determine whether I should jump to a different area, and also what's maybe the influence factor on making this decision of to explore another area or not.
I'll start on this one. All right, so the first thing I'll say is that, so I have a document which I'll share on the Slack channel. That's the broad advice for graduate students around all kinds of things, career and how you work with your boss and all kinds of things like that. Similar document for postdocs. So I'll post those to Slack later today. For permanent staff, I haven't developed that one yet, but that one's coming soon. But anyway, so one way, let me give you my own career trajectory. So I started out in theoretical physics after as an undergrad. Then I went to grad school in theoretical physics because I liked it. And then I went to the same school that my undergraduate advisor had gone to because he liked it there. And I was had zero perspective. I was just following directly in the path that was most obviously in front of me. And then about, around late February, March of my first year in physics, I was like, I really like the work I'm doing in classwork, but nobody seems to have a job doing the kind of work that I like to do. And I started asking around, and all the faculty were like, well, you'll never get a job in that. I was working in general relativity. You'll never get a job in general relativity. That's a dead field. And so I was like, maybe I should. And then shortly afterwards, a letter came from the APS. I can't remember if it was the APS or the AAAS that said something like, we are graduating too many PhDs in physics. Now that the super collider has been canceled, none of them are going to get jobs. And so all of this hit me, in the same week. And I said, oh God, I need to change fields because I'm not going to get a job in physics, even though I like physics. And so I was like, well, I did grow up by the ocean and I'd like to live by the ocean. I got my first job here, which is right by the ocean, as you can see. But anyway, so then I thought, okay, oceanography would be cool. So I'll switch to oceanography. And then I went, I found a bunch of programs to apply to and all that stuff. And then I looked at the deadlines and it had passed 2 weeks before. So I have got 50 weeks to work on my application for the following year, which seems like a terrible thing to have. But I had 50 weeks to just stare at my CV, stare at what I've been doing, think about things I could do to change, to make myself go in the direction I wanted to go. And I did actually spend those 50 weeks doing that. And after that, I realized I should have always been looking for jobs like that, which was, don't at the last minute think that you can bend your trajectory in terms of the job that comes your way. You want to think about preparing yourself for a variety of jobs you'd be interested in. And then when they come your way, you'll be ready. So that means publishing not all in the same niche. It means talking widely to people at conferences, not only the people who are most obviously related to your work, but you also have to stay in one thing long enough to publish and to make a name in that thing before you shift. So it's this delicate balance between how long do I stay in the thing I'm in? I got to make sure I get something notable before I move on to the next thing. But I shouldn't think that the next thing is obvious. And then the last piece of advice that goes along this front is, hopefully all of you will find great jobs wherever you want to be in the world. And, you'll have just the right kind of specialization and support you need from whatever institution it is that you get. What I can tell you is that you will not have all of the preparation you want for that job when it is open. And when you make your application, you're going to feel like they're missing pieces. And you will apply to lots of jobs that look similar, and you will only get one of them. And then, that'll be the one you go to, or maybe you'll get a few and then you'll pick one. But once you get to that place, you will, in retrospect, learn all of the inside politics that was happening behind closed doors and not in public. That is the reason why you were the right choice out of that pile of, hundreds of applicants. So you can't really make yourself perfect for a job, but in retrospect, you will have been the perfect candidate for the job you got. So don't think that you didn't get a job because you're not good. Just know that there's a lot going on in the background that you have no control over. So all you can do is do what interests you, prepare yourself for a broad variety of jobs, and then hopefully the right one comes along and all of the magic happens and you get lucky. Then that's yours.
So I'll try to answer your question the best way I can with a couple of anecdotes. So yeah, what I want to say. Okay, first thing is, of course, everything Baylor said, I think, is very important. But it's very important also not to say, well, I've got to have a job in academia, or that's far more important than the real world. That's, in my view, not true. Actually, during the time that you got this letter from the APS saying there's too many physicists and so on. That, of course, that was a worldwide phenomenon with the end of the Cold War, and actually I started a seminar at the University of Illinois on alternative careers for graduate students in physics, which was at the time the most well-attended seminar in the department. And rather than be a seminar, the thing that I felt was important was to teach people to be self-reliant. So everybody who was in the class had to research a different career, and then give a presentation about it. What the career is, what it involves, what's the training you need, how you get into it, what's it like being in it, can you make a living doing it, etc., etc., etc. And so they did that, of course, and it was a very successful seminar series. In fact, so successful that all the people who were in it all went off into the real world, and there was nobody left to continue it in the future. So that's the first thing. Is really do your homework. So second anecdote is, so the second thing I'd say is, at least for theoretical physicists, I sometimes get asked the question, should I stay in academic theoretical physics, or should I, go into the real world? Should I go into finance, or maybe something perhaps more socially relevant, perhaps? And my answer is, well, you have to do a bit of introspection, just like Baylor was saying. If you care, why is the sky blue? If that's why you're in theoretical physics, or if you are the sort of person who's in theoretical physics because you just like doing the math, well, then if the sort of person who cares why the sky is blue, you're probably going to be unhappy on Wall Street or something like that. If you don't care about that, you just like doing the math, you may as well do a path integral in condensed matter physics, or you may as well do a path integral in mathematical finance. It doesn't make the same difference to you, but one of them you'll get paid a lot more. That's not necessarily the be all and end all, because the thing you're trying to optimize is not your bank balance when you die, but how happy you are. So that's an important factor. The other thing is, of course, along with that, I would say the skills that we have as scientists are incredibly valuable to society. And I just want to echo what Freddie Boucher was saying yesterday in his talk. He didn't have a section which I would have liked him to have done, which is, what could you do? And all of us can do something about the societal problems that we face: global climate change, pandemics, inequity, and so on. So think about that. last anecdote, my daughter did a degree at U of I in computer engineering. In her last year, she switched to statistics. Now she had all the skills necessary to do anything she wanted because data science is the big hot topic. What she actually ended up doing was applying data science for the Chicago Transit Authority, and now she's a senior data analyst. So that was good. It was something socially worthwhile, important, and using her technical skills. Now, how did she get the job? Well, of course, you can imagine there's thousands and thousands and thousands highly qualified computer science and statistics students who are competing for jobs. Well, she got her job because she was writing her CV and she asked, well, she came to ask me, what should I put here on the CV? And I said, well, why didn't you put in the fact that you did goat farming? So while she was a student, she liked goats, and so she went and worked on the goat farm and did that. And there's all sorts of interesting stories. So she put that down on her CV that she did goat farm, and that's how she got the job, because her resume looked the same as everybody else's who'd come from MIT or UIUC or University of Colorado or whatever. But here was somebody who obviously had a diverse and interesting and unusual perspective. And that was useful. That's how she got her job, because that's what differentiated her. And that diversity of outlook was the thing that they realized would be very helpful to their team rather than just cloning themselves. And so that's how that worked. Well, anyway, there's lots of things else I could say, but let me just somebody else.
Well, I'd just like to add to your question directly, and I think there's also a lot of serendipity involved in finding jobs. If you're just planning that straight trajectory, it's never like that. We've been talking about noise along career paths, so there's a lot of noise along career paths. I know in our department, students are thinking they're going to private sector, academia, or into the labs, but it never, when you actually do the inverse problem, it's never like that. So you're, as Nigel was saying, you're trained with a skill set basically, and that's what you're putting forth. But always be open-minded. There's always that serendipity that comes in and job opportunities that turn up that way. So keep an open mind and
I think the only thing I would say is don't assume the perfect job is going to come along at just the right time for you. I mean, it just never, it never happens. You have to kind of have a few, as Baylor was saying, have a few things that you think you could do. You're going to apply for loads, and in retrospect, the one you get will be the perfect job.
Please ask that question again next week when Peter get totally different answers. Peter Whiteman will be back, and he works in private industry. He had been in academia, so I know he'll have some interesting perspectives too.
So just in kind of the spirit of the interdisciplinary nature of the school and trying to communicate scientific discoveries across different fields, I was wondering if if you had any comments on how we can communicate better between disciplines. I mean, hydrodynamics is it's kind of a useful common language, but such things are not necessarily always, they don't exist, at least at the time when we start discussions. So if we could comment on how we can, communicate better to people of different disciplines, how we can avoid reinventing the wheel every time, we want to solve a certain equation or a certain problem across different disciplines and things like that.
Maybe I'll start just on the communication side. I was going to save this for next week, but when I was an assistant professor, I was working on quantum many-body theory, high temperature superconductors, and so on. And I was giving this talk called multi-dimensional bosonization, which was the thing I was working on, and trying to make it into a physics colloquium. And it was a miserable experience for my audience. It was a miserable experience for me. Should never talk about bosonization. So I decided at some point, to hell with this, I'm not going to do this anymore. I'm going to talk about the quantum mechanics of global warming. And so that was a real hit. And I gave that talk maybe 100 times, and people loved it. The audience sort of could understand what I was talking about. And hydrodynamics, of course, was a big part of that. And I think because it's, something that you can visualize instead of like a quantum many body wave function, which nobody can visualize, it really lends itself to visual presentations that you've seen in a lot of the talks here. And so it provides a kind of common language that can really help with communication. And although I think we're still learning how to do this and talking across fields, so I don't think we can claim that we've achieved that, 100% here. We're figuring out, we're kind of groping our way through the darkness, figuring out how to do this. But I think this is a nice subject for this.
Well, maybe I can tell an anecdote if Nigel can tell some anecdotes. I'll tell one. So I think the fact that you're all here is amazing. It shows that you're open you're interested in what's going on in other fields. And in a sense, lecturing here is really tricky because you have to assume nobody knows anything. So you have to think really carefully about what you're going to say. But the anecdote I was going to say is that Brad and I actually started working together. We got together because we were both organizing a program at KITP, and two completely separate programs. So Brad was organizing one on climate, I was organizing one on dynamo theory. And essentially, I would say the crossover between the two programs was pretty close to zero, except for Sasha was my kid, who, I don't know, it was kind of, anyway. Joan Feynman, yeah, Joan Feynman, yeah. Yeah, she was in my program, yeah, exactly. But Brad and I, we had to get together every week to sort out who would use which route, and how useless, our attendees were. We used to chat over a coffee about how useless the people were and how they demanded all sorts of things. And then we just got chatting about what it was we were doing. And it was like, hang on, we're kind of interested in the same thing. And whether you think what we're doing is good or bad, the rest is history. I mean, we've been doing it for 15 years now. So, but it's just being open-minded and then seeking out other open-minded people in different fields who are prepared to listen to what you've got to say.
So I guess, well, so the IPCC is a really interdisciplinary thing. They've got not only all the physical scientists, so glaciologists, meteorologists, and oceanographers, and geochemists, and whatever. We all have to figure out how to talk to each other. Maybe some of us have some cross-disciplinary training. That's one piece. But then the second part is you have to talk to the people who are like the regional resource managers or, the mayor of your city. So there's a lot of figuring out what the communication is about. And I think one important thing, one sort of overarching principle is that you really need to listen carefully. You spend all your time thinking about how you're going to talk carefully and introduce everything and define everything. But actually, it really helps if you can connect to what they're saying and then ask questions about that and then, reorder your priorities to sync up with theirs. That really helps. That really changes the conversation. And once you're off on a good basis, getting started, they'll be much more willing to kind of listen to you spout off and give them all these obscure definitions that they will have a hard time understanding, but to listen to, but only after you've listened to them first.
Well, I don't have much to add to this, but collaboration. Steve had the story where he met with Brad. I mean, Baylor and I, when we first met, had the same thing, and we were in the, pretty much almost in the same field. But Baylor was talking about PV up and down, and I have no clue how PV works and how it moves around. So we're in the same field, but different languages as well. So collaboration is just diving in the deep end and collaborating and learning about what's being done in other fields, how they talk about the same topic. Is also very, very helpful, and going to workshops like this as well. So.
Yeah, I was going to actually say exactly what Baylor said. You should listen rather than talk, and also, the idea that there's disciplinary boundaries, I think, is a bad idea. So, if you're going to work in biology, for example, which I do a lot. You can't just say, well, I'm a physicist, so I don't need to worry about that. That's just, it's offensive, to be honest. So you really have to make an effort to really become, have the real background and study it carefully, and then think, is there a way that what I can contribute is going to be useful in this field, and so on. And sometimes there is, sometimes there isn't. But listening is the important thing, not to be presumptuous. So yeah, so it's a process of self-education. It's not a question of you coming in and saying, here's how it's going to go, folks.
Just to add to that, there are a couple cranky old physicists who don't believe that global warming is a problem, and they've stopped listening. So they're no longer receptive to the huge body of knowledge out there. And so, yeah, don't stop listening.
I guess I will ask a very practical question. So, when you're looking for a postdoc or a future colleague, a professor, like what kind of traits do you necessarily concentrate on? Like obviously research, but are there some things that we might be missing?
The most important thing is to ask former postdocs from that employer what their experience was like. And then don't necessarily believe that their experience will be your experience. But there are many, many people who might be the greatest person to work for ever, but it might be just the place for you to work and be productive. And there are many, many people who are very famous, but whose employees are very unhappy. So you only get to see the ones that are successful despite the unhappiness. And I mean, I think it's not stated enough that if you want to be as productive as you possibly can be, it's extremely difficult to do that if you're unhappy. So make sure you don't have to be perfectly happy. It may not be all, rainbows and unicorns, but it does mean that if every day is a living hell because your advisor is a jerk, you're not going to be very productive. And productivity is what the whole game is in the end.
Like how? Yeah, it was more like how do you choose? Yeah. But that was also useful.
Sorry.
Yes, thank you.
Okay, well, at least I was listening, not talking. I mean, I don't think there's one size fits all as an answer to this. For myself, I can tell you that if somebody writes to me a letter that says, "Dear Professor Goldenfeld, I'd like to be a postdoc in your group. I did my PhD in analytical chemistry at the University of blah, 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 and blah, blah, and so on and so forth." I know that they haven't even looked at my webpage. They haven't even looked at my publications. They don't know anything about what I do. They're just looking for somebody to pay them. Okay. Obviously, if you're going to apply for postdoc, the person who's at the receiving end is going to want to see evidence that you have made a thoughtful application rather than just sent it to some mailing list somewhere. So I look for evidence that the person has made a personal application to my group as opposed to a generic application to somebody who might pay their salary for the next couple of years. So that's one of the things that we look for. And then the other thing is, I would say, is fit. So at least in my group, the way I run it, it's very small. It's also very collaborative, and we have frequent meetings, and we try to help each other solve our own individual problems. And so I also look for not just how many physical letters they've published as a student, but also how well they interact with the other group members. Are they respectful in the way that they talk to people, things like that. And then the other thing is, actually, I don't even care whether they publish physical review letters or not. What I care about is, can they say what it was that they did, and is it interesting to me, and also why they want to work in the group, and what can they contribute to the group as it stands. Well, that's a partial answer. There's lots of things. I'm sure the others here have many other things, but that's just some of the things that come off the top of my head.
No, no. Finish on that one.
So I'll just extend Nigel's. I mean, I think in my area, applied math, groups are not very large. So, fit is, one of the most, one of the key features that we look for. And it's not necessarily that you have, one-to-one that you've been working in the same field, but, in terms of just applying mathematical techniques, having those general skills, that's the way. I mean, are you a good fit from that perspective as well? And also location, where, would you like, in terms of being happy, are you going to be happy in the place you're going to as well? But you've got to be happy if you're going to get a successful postdoc as well.
I would just add, I mean, when I'm thinking of appointing a postdoc, I don't think that there is any substitution for if I'm talking to you, you talking enthusiastically about what it is you're doing, being excited about the kind of thing that you might be doing, with me, having that enthusiasm, and we kind of take it as read that you're all really smart people. So having the enthusiasm and will to do what you're doing is really counts for a lot.
Can I just finish, add another thing to my question? Actually, I want to add another comment, which is, if you apply to me, I actually don't hire many postdocs. The way I do it in my group is this: I'll hire a postdoc if I think the postdoc has a skill set that I don't have, that I want to learn, or I want to bring into the problem that I'm working on. Well, the reason I don't hire many postdocs is this. If I hire a postdoc, then a postdoc has to be able to get results that can get them a job, whatever it is going to be next, within 2 or 3 years. So I have to give the postdocs the easy problems. Then the hard problems are the ones I give to graduate students, because they can really work on the problem deeply and take the time to make big insights and big jumps and so on. And then the impossible problems are the ones I give to undergraduates, because if it doesn't work out, it doesn't do any damage. And if it does work out, which it frequently does, then it's great. And the reason is I think that the important thing is, if you bringing in diverse perspectives into your group is really important. And an undergraduate who works with you may not have been brainwashed by a couple of years of graduate school, and so they'll think differently and ask you different questions, and that's an important thing. So I look for all of those things when I hire people.
Hi, just bouncing off of your answers to the last question, but do you have any comments on transitioning to something different from what you did in your PhD to the postdoc, say from experimental theory to experiment, or just a different field? So, Professor Nigel said you're not going to look at someone who did analytical chemistry, but say, I want to shift from, soft matter to hard matter, or bio or something like that. And I feel like you don't want to be locked in with what you do in your PhD. So just how do you open the doors to more opportunities?
Yeah, so thanks for asking that. That's a great question. So actually, I do look for people who come from other fields, but not ones where they are clearly have just got my name off a mailing list. So I want to make sure that that's clearly understood. And the second thing is, after you've done a PhD, it's a great time to change fields. It's probably the last time you will get, if you at least stay in an academic career, you will get before you get tenure to really change field. And I think many people realize that if somebody comes in and they've, say, worked in an adjacent area or related area, or have some skill set that they want to learn something from you and they can contribute something, I think everybody is really open to that. I'm always advising my students, if you want to go and work in neuroscience or something like that, and you've done a PhD, condensed matter theory, this is the time to go and do it. So I think it's a really great idea to transition into a different field after PhD. And you can always, I mean, you can always come back and you can always change again. I mean, you kind of have another minute of to say of an anecdote. I mean, people always say that, if you're a theoretical physicist or mathematician, you know, you do your best work by the time you're 30, and then after that, you're sort of brain dead for the rest of your life. And I think that's not true. I think what people are mistaking is that people make their best contributions, and not when they're younger, but when they first enter a particular field, because they've got something new to say. And so then the idea is, if you want to stay young forever and keep making new, fresh contributions, you should change fields every 5 or 10 years, or whatever is your appropriate time scale, because it's very refreshing to do that, and you'll have a new perspective to bear. And I keep saying this, it's really important to keep doing that, reinventing yourself, so that you have, you know, new experiences that you can bear. So yeah, I definitely think it's a great thing to do.
I didn't know we were going to get the key to immortality here, but I was going to say that when you're doing a PhD or a postdoc or working in one field, you can begin to work on something else too, and maybe make a connection with another advisor or a collaborator. So when I was a PhD student, I wrote a paper on climate change and the carbon cycle, something completely different. And that so opened this whole new world to me, which kind of was latent when I was this assistant professor, but my colleagues who hired me knew that I had this paper, so that when I started changing direction, they couldn't claim to be completely surprised that there was already this, you know, this hint that something might happen. So, so you can do that too. Yeah.
I guess nowadays fluence, our research is spread all over many different departments. So I was wondering if you had any advice when looking for a job about pros and cons of being in various departments, or how the mindsets might differ.
So they're very different. Fields are really different. So engineering is really different from math, is really different from physics, it's definitely very different from earth sciences. Some of the reasons that they're different are kind of just historical, and then some actually have to do with the nature of the work. So, you know, earth scientists tend to get along because they have to go camping together when they do field work. And so they're really cheerful people, but they also don't have a whole lot of patience for getting really deep into the mathematical aspects, at least compared to other fields. And so that, you know, you can think about how that fits for you. I found physics to be more competitive than I was comfortable with, which I didn't know that was the case when I was in physics. But after leaving physics, I, in retrospect, felt like that was something that was probably, you know, making me feel bad. But then, but I didn't leave the tools behind. I just, you know, sought a job with a different group of colleagues. So I think, you know, and now here I am back here. So I obviously didn't even really ditch physics at all. I just was, you know, taking a different angle to looking at the different part of the physical world. So, you know, it's hard to guess. And I think that, you know, the differences are just as big between like a soft money position and a hard money position at a research lab, or a teaching focused job at a small college, or a research focused job at a large university. Those things have big emotional tolls that come along with the work itself. And, you know, everybody's different. So people are happy in all of those circumstances. So it's a little bit of introspection that's required to figure out what'll be a good fit for you. And another thing about not only changing fields for changing postdocs, but it's not a bad idea to go to a institution that's quite different from the institution you were at as a PhD student or as an undergrad, and experience a little. So you know, go to a research lab for your postdoc when you were at a university as a PhD or something like that. That can help you find out what those differences are among the fields and among the institutions you might work at.
So I'm not sure, are you applied math or physics or physics currently? I'll say, well, applied math, in fluids, there's not a whole lot of departments doing that in this nation or abroad. So we're always changing our hats, trying to see where we can sneak in and get jobs. So every opportunity that's that's available to, that lends to our skill sets in fluids in different departments, if the culture is good, I think we would try to, students in my department are always trying to apply broadly and widely that way.
I have a quick comment. I don't know if it really answers your question. Having worked in many different fields, material science and biology and engineering and physics and so on, I've always stayed having appointments just in the physics department because I felt that if I woke up one morning and decided to work on, say, black hole dynamics, which I did actually, and spent some years doing that, nobody will mind. And then the next, I work on high temperature superconductivity or biology or whatever. So for me, depending on the style that you have, physics department is a very good fit because it's gives you a lot of license to work at the boundaries with other disciplines. And that's what I think is the most exciting science is done at the boundaries between disciplines. On the other hand, if you're really deeply committed to a particular type of problem, you might feel that you have to be really in that department in a way that shows commitment to the problem and enables you to get the respect of colleagues and people listening to you and things like that. So.
Yeah, also maybe just a quick comment, it could be country dependent as well. So people who sit in applied math departments in the UK, perhaps in the US, they could sit in engineering departments or sciences departments or whatever. So, if you're going to go cast your net abroad, make sure you work out the culture of. So in the UK, for example, a lot of fluid dynamics is in applied maths departments, and this goes all the way back to bachelor. And his influence on the UK scene. The other thing I would say is, from my perspective, we have at Leeds, we have a Centre for Doctoral Training in Fluid Dynamics. And one of the rules of that Centre for Doctoral Training is that any student must have a supervisor from more than one school. And so therefore, I spent a lot of time recently, supervising students with people from engineering, from people from physics, from people from earth and environment. And Baylor's right. I mean, you can tell. I mean, if you shut your eyes, you go, I'm supervising this guy with an engineer, because he wants the answer tomorrow, and he's not quite worried about how accurate it is. For example, if it's good enough, it's good enough. And so it's worth going and kind of thinking about what what you want to do, and how you want to do it, and how it's typically done in these departments. I'm not dissing engineers; they have to do what they have to do.
Hi. My question is also related to this changing fields, but I want to know if you're thinking about staying in academia, going into industry, is that like a once done, that's the decision that you've made, you can never switch back? Or is it like I can go in industry, maybe work in some data or some machine learning or something? How does for a few years, and then is there a way to come back into academia, maybe do a postdoc later? And how does the academic community look at such applicants, and is it very accepting of it? Because maybe you might not have papers related, which might be like a major thing, but in general, is that accepted? Or like once I make a decision to go into industry, that's it, like I can't come back?
Well, it's certainly not it. I mean, we've just appointed somebody who's spent 7 years in industry and has just come back in a position in applied math. So it don't feel like you're kind of, whatever decision you make, that's it. I wouldn't kind of switch around, on a whim, but don't ever feel like you can never make the transition back. At least that's my experience. It may be different in the States, so these guys might.
So, if I take my department as an example, we have multiple entry points, so if you're trying to transition back into academia from industry, sometimes a student comes back to do a PhD and start along that way, sometimes it's, gaining a postdoc, but we have several faculty whose origins are not, beginning with applied math. They've come from very different, from industry, Exxon, Schlumberger, and things like that. So the multiple entry points in terms of getting in. It's not a given that you have a traditional pathway or traditional resume in terms of what gets you, what gets you at these multiple entry points. So I think just always keep the doors open and think thoughts open as well.
I think it's a really tricky question what you're asking. I would say that my experience has been that people who have been in the industry for a while then come back and do a postdoc. It is very difficult for them to get a postdoc and then to get faculty positions. It's not impossible, but I think it is more difficult because it makes them. It gives the impression to some places that they're less competitive because they're further on in their personal career. On the other hand, as you said, sometimes they're bringing with them really relevant industry experience that can actually be an asset. So if that's the case, then of course there's then it is possible to go back. But in general, I think once you've gone out of academia, it is more difficult to come back and then proceed to have an academic career. That being said, two of the best students that I ever had were people who had gone after their undergraduate degree, had gone out into the real world and done stuff like that, then came back to do PhD. And they were great because they were sort of more mature. They knew exactly why they were there, what they wanted to achieve. They had a lot of experience and some different perspectives and skills than the regular graduate students. And so, that it may be that the entry point is the one that one has to think about. I think also going back again, a personal anecdote. When I told you about what happened with the job crunch that you were talking about in the early 1990s, so I was advising students about how to get a job in the real world. And saying the real world needs logical, educated numerates, people who can communicate and understand sophisticated ideas. But of course, I was just sitting in my university physics department, not doing any of that. So I actually took a leave of absence from the university and went out into the real world. I wasn't paid by the university. I started a software company, and I actually did get real world experience for about I don't know 5 to 10 years. I was working closely with that company. Initially developing software that's used by financial institutions, and then developing software for medical physics. And that was extremely broadening. That really changed my perspective as a scientist. I of course, came back to academia after doing that. And I was lucky enough to be at a university which allowed you to do entrepreneurial leaves of absence. So it isn't, your career path is not set in stone. So I think you have to, but if you're going to make these transitions, you have to choose them very, very carefully and be very thoughtful about what you want to achieve when you do them. The postdoc is really the sort of gateway drug to being a professor or something like this. And if you're not going to do that career, then unless you're getting some very specialized training that you think you might need in the future, there's probably not much point in doing it. So. Does that answer your question, or is it helpful in some way?
Thank you. May I ask a second question? Actually, my experience, I'm from earth science. I did my bachelor degree in meteorology. And I found that it seems that the larger the meteorology department is, the more people are more conservative and not paying too much attention to, get involved in applied math. So, but I know it should be improved. And now I'm at Stanford. Stanford has a very small earth science. So I got the chance to interact with many engineering people. So I'm wondering, because in University of Colorado, we also have a nice Department of Atmosphere and Ocean Sciences. So for an institute with a relatively large atmosphere and ocean, how do people connect more to applied math or fluid or physics? Yeah, what's your secret or experience? Thank you.
So yes, I think you're absolutely right. These very big programs. So I went to MIT Woods Hole as a PhD student, which is one of the biggest, PhD granting oceanography institutions in the US. And everyone there really knew what their niche was. And in fact, there was a little bit of trouble if you decided you wanted to drift a little out of your niche over to try something that might be somebody else's territory. There was a little, oh, no, you don't really know what you're doing and that kind of thing. So it could be done, but you had to really kind of commit to sliding around. And so I was fairly, single-minded about what I thought was good, the kind of science I wanted to do at that stage. Then when I came to Colorado, I remember I was sitting over at the sink over there with Wei Jing Han, who was the one other oceanographer at the time in the department. So then the atmosphere and ocean sciences department was very small. Now it's gotten bigger. And she said, well, of course, you'll be teaching in general introduction to oceanography, and you're going to cover this. And I thought, I don't know any of those things. And so anyway, off I went to figure it all out, with the 1 month of summer that I had before I started teaching in September 1st or whatever, on this wide ranging set of oceanography ideas. And so it was terrifying at the beginning. I had to learn the difference between a dolphin and a porpoise, which I still know, but I didn't know then. But then I realized that the other side of that was that there's a lot of freedom, because nobody told me, you can't do climate change. You're not part of the climate group. You can't do small scale oceanography. You can't do large scale oceanography. So this conception of all the scales from the climate scale down, I started developing because there was nobody else to bump into at a different scale. And so through broadening the kind of teaching I was doing here to try and bring, get the students exposure to every scale all the way up and down. I'm not sure that there's anywhere else you could have done something like that if you weren't sort of isolated. So there are advantages to both sides. On the other hand, there was nobody else to talk to unless I went up the hill to NCAR or went somewhere else for a conference. So you have more freedom, but maybe less collegial interface. And so there are advantages both ways. But so I think, it's hard to think about, but Keith should also address this since he saw this whole process happening too.
Yeah, well, I would say in applied math, we're sort of set up that way, so, we have a large affiliated faculty, and, in our student training, it's an expectation to go out with faculty and students to work with scientists in other disciplines, actually. So it's really, that's what we're expected to do. It's also, in terms of a funding part of view, it's a very lucrative thing to do, given that applied math funding is not as lucrative. But yeah, so this is the tradition for an applied math department, at least the one we have here, and this is how I actually met Baylor. Yeah. So, and we've shared several
many
proposals. So
yeah.
Any more questions? Probably this is a good place to stop. So thank you for all those questions, and have a good week.